All right, well, hello everyone, and welcome to tonight's stream. I am just setting up here. Give me 1 second, make sure everything's working properly. And today we are continuing from where we left off yesterday. We're going to do 2.7. Okay, so general rules apply as usual. I am going to read through the book, and then afterwards I'm going to do the equations. So if you wanted to follow along, or if you want to read for yourself, the book is located in the video description. It's in the Creative Commons. Download it and get the book right now. It's a very good book. Book of Proof, 3rd edition by Richard Hammock. All right, so now we are reading 2.7. Quantifiers. Using symbols such as and, or, not, implies, and if and only if, we can deconstruct many English sentences into a symbolic form. As we have seen, the symbolic form can help us understand the logical structure of sentences and how different sentences may actually have the same meaning, as in logical equivalence. But these symbols alone are not powerful enough to capture the full meaning of every statement. To see why, imagine that we are dealing with an infinite set, x, such as containing x1, x sub 1, x sub 2, x sub 3 of integers. Suppose we want to express a statement every element of x is odd. We would have to write p x of 1 and p x of 2 and p x of 3 and so forth, where p of x is the open sense x is odd. Remember, we're using p's and q's here for statement 1, statement 2, or essentially when we do logic, we use the form of p and q, p or q, and so forth. And these are, you could substitute a sentence for that, or a statement or a fact, or a cause and effect, for example. Anyway, where p of x is the open sense, x is odd. So if you wanted to write and express there's at least one element of x that is odd, we'd have to write p x sub 1 and or p x sub 2 or p x sub 3 or p x sub 4. By the way, I'm not writing any of this down simply because this isn't how it's done. In the sense that if we're doing large set, we're actually getting to the part where it's actually done. That part I'm going to start writing down. The problem is that these expressions trail on forever. To overcome this defect, we will introduce two new elements. And then we have the turn A, or upside down A, and then the turn E. And these symbols, the turn A stands for all. This means for all. I believe it's called the universal quantifier as well. So in this sense, these are quantifiers, and for all means universal in this case. So for every, this is the universal quantifier. And the other quantifier, E, turn E, stands for there exists. So the turn A, universal quantifier, refers to all, it applies to all of them, in other words, for all such cases. The turn E represents there's at least one such case. All right, so now, and that was just my own interpretation here. Getting back to the book. Okay, so now we're going to write universal quantifier x such that the set of x, so for all of x contained in the set of x, there exists a set where, let me read this one more time. There's at least one element of x that is odd, every element of set x is odd. This is read as okay. So basically what we have here, let's read it. Every is right here. and an element, in this case, element contained in the set of X, element of set of X is right here, is odd. Now this part right here, the last part, P of rounded of X, we simply made that earlier. We defined this, the P of X, we just simply defined that. It could have mean anything. It could be they're all even, for example. This was defined earlier saying that, here we go. So that was defined that way. And again, it doesn't have to be defined that way. We could define it some other way. But in this case, when we do that, we can work with it. Now, we're going to do the next part. Now we're going to work with it. I'm going to say exists an X, exists an element in the set of X such that there at least exists one element in the set that is odd, basically. There is at least one element of X that is odd. That is how it's written here. Okay, so we have all right. So yeah, that's what that means. And yeah, we're going to keep that in mind. These quantifiers. One we have, this is the universal quantifier, and this stands for, what is the E-quantifier? Let me see what the technical term for it is. I guess exists quantifier. There exists a quantifier. I gotta look it up, see what else it's called. Usually these things have multiple names. All right, I'll do that later. I'll just call it turn E here. This is a statement for every n containing integers. 2n is even, can be expressed in either of the following ways. For all of n of the integer set, 2n is even, or all of n in the integer set, there exists an even. Wait a minute here. What is the E? That's interesting how they wrote that. I wonder if they define that differently. All right, well, let's see what they did here. So we're going to have to play around with this a little bit. This is quite a bit different than the stuff we've been doing, so let me just add more layers here. Turn this one off. There we go. And here we go. We got 2.7. All right, so we're going to say, let's write a sentence. And for every n containing the integer set, 2n is even. And then we're going to say for all n containing the integer set, 2n, I understand now, is even. So now what they did is this. Remember how we said that the P can be defined as meaning something? You can also, in this case, use an E to mean even. So we're going to go even like this. We're going to go all of n containing the integer set, the two n's are even. Okay, so this becomes that. All right, just an even some more simplified form. All right. Now they didn't define the large e as even, but going off what they did earlier, I guess we can also do this. I'm just gonna write something of my own here. And let's see, we're gonna say here. Okay. P of, let's see. P of 2n. That would make sense. Something like that probably should work. I defined the P, going off what we did earlier with the P of x as being defined as x is odd. We're going to say P of 2n is even. Let's see here. Anyway, or perhaps we might have to do like this. I'm just playing around with this right now. Just getting more comfortable with this notation. Okay. Oh, not what I wanted. So I would think that you can do that as well. All right, but let's continue. Let's just get through this and get to the next part. See what we have. All right. My goal is to do about 5 pages a day. I am taking this class. So yeah, retaking this class. I didn't pass it the times that I took it before. I've taken this class twice, actually. Both times I dropped it to focus on work. I'm a professional landscaper / handyman, and I'm also a figure skating coach. So work keeps me busy. But hey, that's what you got to do. So I am still very curious, and I'm pursuing a double bachelor in computer science and pure math. It's a long-term project, but I do have an associate in computer science. Anyway, I'm at Westchester University right now, and yeah, fun times. My life is interesting. Likewise, the statement, there exists a subset of x of n for which n, let's just write this whole thing. There exists a subset x of the natural set for which the cardinality of x, it could be a cardinality or absolute value of 5. Let's see what they're actually trying to say here. Okay, so we're talking about sets, so it would have to be cardinality. So in other words, let's just give an example real quick. There exists a subset of x of the natural set for which the cardinality of x would be 5. So it would be something like this. I just created a 5-item set. It could be anything. So basically, the cardinality is the size of the set. There's 5 items located inside the set. They're all a subset of the natural set. So yeah, that's just an example. It could be any number. Another one could be like this. It could be... Notice I'm not using 0, and I'm not using any negative numbers. The natural numbers do not contain 0, and they don't go into the negative. Those would be integers. And we've covered all of this in previous chapters. That was all in chapter 1. If any of this doesn't make sense, now we're quite a bit into the book, even though it's only 50 pages. Go back and rewatch some of the other stuff, and then try it yourself. I would say that even a high school student should be able to pick up the very basics of this book and work their way through it if they have the time for it. It is very dense, but if you go slow and you take your time to understand everything, you can get through it. It's a good book, very good book. Anyway, so let's translate the sentence here. There exists a subset of X of the natural set for which cardinality of X is 5. So we're going to say there exists, and they have the examples below us here, of the subset X such that, let's see what we're going to say, not such that, that's fine. There exists a subset of X, so we're going to say exists subset of X, and we're going to say X is a subset of the natural set, and the cardinality of X is 5. Now, we are really shifting gears compared to the stuff we were doing yesterday. This kind of goes back to what we did in previous chapters. So, yeah, this is more along the lines of what we did in chapter like 1.3 through maybe 1.6, something like that. Anyway, so it takes me a minute to just kind of like change the gears and get going here. Let's try a few more versions we have. What else can we... Just writing down what they have here as examples. Exists a set X, which is a subset of the natural set, and the cardinality of X is 5. Okay. Another one we could say exists the subset X containing the power set of the naturals, and the cardinality of X is 5. So yeah, remember power sets, you have your singletons, doubletons, tripletons, quadrupletons, and then I guess quintupletons. So yeah, that's what it's getting at. I would probably use the middle one. It's a little less involved, but the first one's good too. The power set, yeah, I mean, like all of these are all good. It's just you gotta work your way through them and to get comfortable with them. Let's see here. Unfortunately, I'm looking at this thing. There's only 10 questions, and of course, we only do the odds because we don't want to damage the integrity of the book as a teaching resource. We want to do the ones with answers in the back. But this is the kind of thing... one thing I'll tell you about math very quickly is that anything that's really useful, you're going to do it like 50,000 times. So if you feel like, oh, there's just not enough questions here, or trust me, if it's important, they will drill it into your brain. Anyway, so that's good. That is, if you take the time to do the material. The chapters, the way they're laid out, they're meant to, like, I would say, speaking as one, to make it college student proof. You just got to do the work. Do the work. Study. Read every page. No skipping. All right. So then we have the symbols turn A and turn E are quantifiers because they refer to, in some sense, to the quantity, i.e., all or some of the variable that follows them. Symbol turn A is called the universal quantifier. Turn E is called the existential quantifier. E exists, and A represents the universe for all. For all, this is called the universal quantifier. Okay, and for turn E, turn E, that is called existential quantifier. Okay, good. All right, so now, very good. Statements containing them are called quantified statements. A statement beginning with the universal quantifier is called a universally quantified statement. One beginning with the existential quantifier is called an existentially quantified statement. The following English statements are paired with their translations into symbolic form. Here we go. Okay, here we go. This is example 2.5 on page 54. Every that is odd is even. So we're going to say every in this case. We're going to say all naturals, or all n. N refers to whatever in this case. N is some quantity or some number. And we're going to say for all numbers in the integer set. So now we have nailed it down to say that it can be positives, it can be negatives, it can be 0, but these are all whole numbers. So, and then we're going to say not n is odd implies n is even. Okay. Well, I probably wouldn't have worked that out on my own. Okay, that's good though. That's good. So we have the universal quantifier, all natural, or I shouldn't say that. Okay. All n numbers that are part of the integer set that are not odd is even. And let's read it one more time. I'm going to try to read each character now. Universal quantifier. All numbers containing the integer set, not integer is odd, implies n is even. Okay. Just, it takes some time to like drill this stuff in your head, but it gets there. And if you don't have a good feel for it, that's okay. Just keep doing it. Keep doing it. You don't need a full and concrete comprehension of all this stuff. I certainly don't have it. But you just have to keep plugging away at it. This is very important. You don't try to gain some philosophical transcendence and full and complete understanding. Just power through it until you're able to work with it, and eventually it'll start clicking. But you have to put pen to paper. Nothing will happen if you just sit there and just listen to streams or just try to work it out in your head. There's too much is lost. You need to work through it. Put pen to paper. It's very important. There is an integer that is not even. Okay, so we're going to say, actually, let's do this other version of it. Oh, integers containing all, okay, instead of saying n containing integers, we're just going to say all integers. This is just going to be integers. Just going to read it like that. Instead of all numbers containing integers, all numbers part of the integer set, we're just going to say all integers, not, in this case, odd, implies even. So this usage, big O and big E for odd and even, I don't know, maybe it was defined somewhere where I missed it. I don't think I had missed it, but yeah, let's roll with it. As long as you can read it and understand what's going on, that's fine. Yeah, like, and that's something else. Like, if you were to write a proof, you can, in principle, throw in your own characters, and just for the sake of the proof, you can say like something like this. Let's say, let's try U universe. So like something like that. And so for the sake of your paper, you just defined it that way, or your proof. But just like, don't do it willy-nilly, of course. It has to have a point. You want to be efficient with your usage. Don't meander when trying to prove things. Otherwise, you might get yourself in a cul-de-sac and you'll never get out. All right, so let's see here. Let's do some more. Let's read this. There we go. There is an integer that is not even. Exists a number containing the integer set. There's just an integer, and that is not even. So they put periods at the end of these. You gotta look for these little things. These are technically sentences, even though they're symbolic logic. They are still sentences, so I guess they want periods at the end of them. All right, that works. All right, let's go to the next page. Okay, so we're going to say this one. Given any two rational numbers, A and B, the product AB is rational. So this one right here is probably going to be one of the first proofs we're going to have to do, or something to that effect. Well, we're going to have to prove for all cases, no matter how large the numbers are going to be. We're not doing that right now, but yeah, this is a way how to do this. But right now, all we're going to worry about is just writing in symbolic logic. All A and B, in this case it applies to both of them, containing rationals, A times B also contains rationals. So the rational set are numbers that you can write them as a fraction, and they either have a terminating number. For instance, like if they go like you divide it by like, I don't know, say like 1/3 is going to be 1.333333, right? And that's forever. So that's a repeating set, even though it's infinite. I believe that's still part of the rational set. An irrational one would be like pi, which is non-terminating, non-repeating. So anyway, just a quick thing. And remember, I'm a landscaper and a handyman and a skating coach. I am not a mathematician, so there's plenty of things I say which probably contain large omissions or not fully strictly ballroom when it comes to math. Just keep that in mind. I'm a student. I'm doing this as my study session. All right, so yeah, let's continue. Given a set X such that, but not limited to, naturals, integers, rationals, etc., a quantified statement of the form all of X containing the set X are, and P in this case, what do we define P as? Oh, right, we're just using P of X. In this case, we haven't defined P yet. Is understood to be true if P of X is true for every X contained in the set of X. If every integer or number contained in the set X. In this case, by the way, they're doing this. X contains The big X refers to a type of set. It's just a set, right? And the small x refers to any number. So in this case, the x would be, there can be any different numbers, and they all can be organized as a big set inside the x. If there's at least one x contained in the set x for which p of x is false, then all of x contained in the set of x, p of x, is a false statement. Similarly, exists x within the set of x where p of x is true, provided that p of x is true for at least one of the element of x. Otherwise, it is false. Thus, each statement in the example 2.5 is true. Here are some examples of quantified statements that are false. The following are false quantified statements are paired with their translations. Every integer is even. So yeah, that is, well, you know what? Let's just write these out. I'm gonna qualify these by saying these are false statements. Here we go. Okay. Every integer is even. Every number contained in the natural set, even. Okay, cool. There is an integer n for which n squared equals 2. Nope. That's very easy to prove. Just square root the n squared. And yeah, it's going to be either negative root 2 or positive root 2. So, here we go. N squared equals to 2. Okay? We just have to write this false statement. Exists. And we're going to say there's an integer. So exists and contained in the integer set where we just write the statement. N squared is equal to 2. Period. Okay. And yeah, period. These are sentences. So exists an integer, and I just underlined that, where n squared equals to 2. Again, false statements. For every real number x, there is a real number y for which y squared is equal to x. For every real number x. So like if x is pi, then y is y squared. That's probably how you would prove that. I mean, I don't know. Let me think about this. Oh, no. It's simpler than that. Okay, how do you prove this statement? How do you prove that it's false, right? We're talking about real numbers. So we can't use imaginaries. That's the trick. We cannot use imaginary numbers. So this is how we prove it. Y squared is equal to Now, this is not a formal proof. I'm just going to show you this is a false statement. Well, what if we're going to say let x be equal to -1, and we're going to say y squared equal to -1. We're going to root this. Root y is equal to root -1. And you can't do that because this is equal to 1 root 1 I. And yeah. And the square root of 1 is 1, as I recall. Yeah. Which makes sense because whether this would be, which is equal to, adjust this a little bit, 1 I. But that's not I and is not in the real set because 1I is not contained in the real set. So yeah, basically I just demonstrated for you what that number would actually be, but it took me a minute. I was thinking, because technically I was thinking, okay, well, what about a number that, like, because you try to break numbers at this point. Like when you think about what a number is, oh God, this is like a philosophical question, but the more you work with math, numbers, you start to see them differently. The more you work with anything, you start to perceive things differently. But numbers are things that you can start to just take apart and put back together inside your head. You know, you think of like numbers that can just right away, you say 2 to the 3rd power is 8, right? Or you can say if third root or cube root of 8 is 2 and so forth. You could just like roll numbers around, and certain numbers you know, like you could say like 169, that's 13 squared. You just know that, right? You know, like, or root 169 is going to be 13. And there's much more numbers than that. Like the more you work with them, the more things become familiar and just kind of roll them around within your mind, and they disassemble and reassemble, and then, you know, you have various composite numbers and prime numbers and so forth. Now, like, obviously you won't have like a true understanding of every single number. That's impossible, not even close. But just like on these smaller numbers, and you will right away think, well, how would you break it? You have to break out of the real set, and then you just remember, oh yeah, you can't root -1 in the real set, so all you have to do is just get to that. And yeah, that's how you do it. Anyway, continuing on. We didn't actually do the thing that it wanted us. I just went off on a random tangent. Welcome to math. Alright, let's actually write down what they wanted us to write down here. For every real number x, there is a real number for which y squared is equal to x. So we just have to write down this false statement. Let's see here, we have all of x for all numbers x in the real set, there exists a y also contained in the real set. Now notice we didn't do of all x comma y, because that would mean all x's and all y's. There just exists at least one in this case, where y squared, just writing down the equation, is equal to x. False statement, but yeah, that's how it's done. And all the stuff, we're going to have to come back and hit these pages probably in subsequent chapters, just because, just like it takes time to really get comfortable with any new notation. So yeah, these are good references examples. Even though these are false statements, as a reference, they're still giving us things that we're going to need. Given any two rational numbers, a and b, the number square root of a and a times b is rational. Okay, so any two rational, that's an easy one to break also. Any two rational numbers. So we know that root 2 is not irrational. Root 2 is about 1.41, it goes on forever. This is irrational. So if any two rational numbers, all right, so we're just going to say a is equal to 1, b is equal to 2. Square root of 1 times 2 is root 2. That is an irrational number, and we're going to say root 2 is not contained in the rational numbers. So yeah, that's another easy one to crack. But again, it's just like root 2 is a good one to use to keep in the back of your head, just as like you remember how you can't square root -1. Root 2 is a very easy one that does not exist in the rational set. So that's just a good convenient number. But again, I am going off on a tangent. I didn't actually write down what they wanted us to write down. For all A and B containing the rationals, root A and B, A times B, also contains a rational, which is a false statement, but there we have it. These are all false statements, but useful. All right, we're continuing on. Example 2.7. Okay. Hang on a minute. I just jumped to the next page. That's really interesting. 2.8 does not actually have any questions. Just have to read through it. Okay, that's fine. We probably can cover that tonight. Let's get through we're in example 2.7. All right. So this is chapter 2.7. Now we're in example 2.7 on page 55. When a statement contains two quantifiers, you must be very alert to their order. For reversing the order can change the meaning. Consider the following statement. Just going to read these three symbols as one word or one sentence. We're going to say all, and this we're just going to say this is going to mean integer, or we're going to say all numbers in the real set, or all reals. Let's just say all reals. Yeah, that's fine, because technically it's all reals. We're just going to say all reals. We're going to say, turn that E, exists a Y for all of X. I'm just going to, you know what? I'm just getting ahead of myself here. Let me just take this out of here. Just do the sentence. It'll be easier to comprehend. Okay. For all of X containing reals, exists Y and where Y cubed is equal to X. Okay. So for all reals exists a Y where Y cubed is equal to X, or X in this case would be cube rooted to get us the Y. So for instance, if Y is 2, then X would be 8. Cube root 8, you get the Y, which is 2. I'm just thinking how to crack this one. See, like if you use a negative number, you would still be able to get it back, because the to crack a real set, you need a square, and then you can get the I. I don't know, maybe. But we can still, let me see here if it was, what if X equals to, let's try -1, right? And Y to the third power would be, so in other words, we would have to, I'm just thinking about this here for a minute. We'd have to cube root, all right. I have to really think about this. All right, well, but I'm getting off topic. let me just, instead of cracking sets, let's just get through this example. I mean, this stuff is just too fascinating. It keeps distracting me. Anyway, so this statement is true for no matter what number x, there exists a number y. So yeah, it's kind of what I thought. Like I said, this is why I didn't want to try to spend 2 hours trying to crack the real set, because yeah, you can always do this. So let me show you how they got this. So when we have y to the third power is equal to x, so then if we can do this, we can cube root, and these two cancel. Cube root x, and then so now y is equal to cube root of x. So that's how you do that. Okay. Yeah, so cool. Now, I reverse the order of the quantifiers to get the new statement. So getting back, so we're going to say exists an x in the real set for all of y, where y cubed is equal to x. So, my apologies. And let's see here. Oh, wait. Exists. So we have to also try to clear my throat a little bit. I would stream all night if my voice wouldn't start cracking at around 11. And the reason I stream late is because I work all day. I was at work. I started around 10. I started a little later today. I had a few things I had to do at home, but I worked till 9. Usually I go to about 8 to 9. And, you know, traveling and so forth, you end up working about 10 hours a day. And I work 7 days a week. But hey, you know, running your own business is worth it. And getting back to what we're doing here. Right. This is where, yeah, I changed the meaning around. Did not need to do that. We don't want to change the actual meaning. So, for exists a y for all of, within the reals, for all of x, where y cubed is equal to x. So what we did was, we took this, the all of x, and we moved it to where the y was. And then took the exists a y and we moved it. So that's how we did it. We just moved them around. That's important because then we don't have to mess with the equation. Otherwise, we'd have to rewrite the equation here. This would have to change. Because we can still, just like I did here, I rewrote the equation to show us what the y would be. You know, if you just wanted to throw a y, any y, and then we would know what the version of x would be in this relationship. Anyway, so that's how you do it. Okay, so yeah, let's see here. This new statement says there exists a particular number y with the property that y cubed is equal to x for every real number x. Since no number y can have this property, the statement is false. Two statements above entirely have different meanings. Oh, I see what they did here. So I wrote it correctly, and then they wrote it incorrectly to show what an incorrect statement looks like. Okay, right. So yeah, this is, let's see here. This is false. False. Okay, nice. This new statement says that there exists a particular number y with the property y squared equals x for every real number x. Since no number y can have this property. In other words, look, what is this new statement saying? This saying that there exists a y in the reals for every x. That means there is one number x that is so magical that, let's say x is going to be 2, right? And then y cubed would give us 2. Or x can be 5 or 8. But this one magical number can create any number you want it. You just have to cube it. Take it to the power of 3. So no, it's like a 1-for-1 type of relationship. In this case, you can't have a number that's gonna spit out like a million different numbers off of this one relationship, because this relationship, it simply means you take one number, you raise it to the power, to the third power, and it pops out the result number, which is the x number. However, this is saying that every possible number will result from the one entry number, this magical number that you put in y. That's not the case. Let's see if we can write this correctly, though. So they gave us the false statement. Let's actually write this correctly. So we're going to say exists an x within the real set for all of y, where y cubed is equal to x. Let's see if this is correct. Exists an x within the real set for all of y. No, wait a minute. It's the same problem. You still also is going to be false, because that means for all of y cubed, this one magical x number now, also false. So you got to be careful how this works. Okay, let's just continue here. Yeah. Quantified statements are often misused in casual conversation. Mostly you've heard someone say, all students do not pay full tuition, when they mean not all students pay full tuition. While the mistake is perhaps marginally forgivable in casual conversation, it must never be made in a mathematical context. Do not say all integers are not even, because some are, of course, because that means there are no even integers. Instead, say not all integers are even. Remember the not. Let's write that right now. They're not giving us this one, but we're gonna try to do this. Not all. We're gonna say x containing the integer set, and then we're gonna say e of x. I think that's how we would do it. Let me go back and look real quick here at what we have for examples for even. E2 of n. Not all x containing the integers. Yeah, that looks right. And period. Gotta put that period there. Okay, now remember, this is not. I'm saying that's not. That's important. Symbol right there. Okay. Good. Let's continue here now. So that was just something that I just threw out there just for the sake of practice. You know, I'm trying to really let all this stuff sink in, because I have to take this class. You know, I've already failed it twice on account of work. So at this point, I want to show up there and be like, hey, professor, I did all of the even numbers. Yeah, here's the proof. Here's the, I don't know, 100 hours worth of streams. I don't know. We'll see. But anyway, let's see where we're at. All right. And hang on a minute. I'm on the wrong slide. There we go. Okay. So now we have gotten to the exercise section. That was, wow, it took me an hour to get through. Now, there's some meandering involved, but that only covered 3 pages. Yeah, but this is like, since we really switched gears, I had to go a little slower and really try to suss it all out. Otherwise, it's because there's not that many questions for us to answer. Well, let's do them right now. Here we go. We have one is all numbers, all x containing the real set, so all reals, all x containing the real set, x squared is greater than 0. So you're saying for all of x containing the real set, x squared is going to be positive or greater than 0. So let's just think about this for a minute. If x is negative, x squared is going to give us a negative number. If x is positive, x squared is going to get us a negative number. So right away, you think that the answer is true, right? But the reality is it's false. Now, take a minute and try to understand why it's false. It's right there. The answer is written right there for you. And the answer is 0 because it's greater than 0. All we have to do is put the 0 in x squared, and 0 cannot be bigger than 0. So that's the answer. So this is false. And we just have to write this in English sentence and say whether it's true or false. Oh. We're going to say, oh. How do we want to write this thing now? Second here. Every real number x. There we go. Oh, for every real number x, and we're just going to put the equation in there. X squared is greater than 0. And we're going to say this is false. False. 0 squared. 0 is not greater than 0. Okay. So, yeah. And that is the answer. Whether or not I wrote it how they want it, that I don't know. We're going to find out. Let's go. All right. Okay. Yep, there we go. Same as false, reason is 0. But it's not true that 0 squared is greater than 0. Yeah, and what they wrote it is for every real number x, it follows that x squared is greater than 0. Also, the square of any real is... And here's how I wrote it. For every real number x, comma, x squared is greater than 0. So instead of writing it follows that, I wrote it word for word exactly how they wrote the first answer, which makes sense. I was just looking at the previous examples that we were playing around with and looked at the structure there, so that wasn't hard to figure out. Let's continue. All right. There exists number A. There exists a real number A. Number A. And exists for all of real numbers x such that x squared, a times x is equal to x. There exists a in the real set for all of x such that, one more time, exists a number a in the real set such that for all of numbers x containing the real set, a times x is equal to x. One more time. There exists a number in the real set for all of x, for all of numbers in the real set, such that a times any number in the real set is equal to x. So yeah, this is true. And that's simple. A is 1, right? 1 times anything is that number. So if 1 times 1 is 1, 1 times 0, in this case, the x, the numbers that we keep changing is not the A is 1. And we're going to say this right here. A is equal to 1. And then, so we can say A times, anything will give us that number that it multiplies by, be it positive or negative. So that's a true statement. Let me spread this out now. There exists a number. There exists a real number A. Let's just say a real number. There exists a real number. There exists a real number all right, well, we're going to be more stringent. We're going to say there exists a real number A. The second A is not really necessary, but because they use the A, like if they used Y, we would say there exists a real number Y, for example. For every real number X, and we're going to say such that A times X is equal to X. Or we could have just left it at the comma, but that's fine. And we're going to say this, yeah, we already answered the truth of it. Okay. All right, let's take a look. Let's see what the book says. Answer. Yes, true. Consider A equals 1. Yeah. By the way, all this stuff that, like, I didn't look at the answers in the back of the book. I'm doing it on the fly. But again, this is, like, it seems like this is some crazy numbers, but really they're giving us very baseline examples of things. You do enough math, you're just going to know. You're like, from anything else that you do where it's just, these numbers, certain numbers that you work with, you're going to find that certain numbers have certain properties, right? Like anything times 0 is equal to 0. Like you can't divide by 0, for example. That's undefined. What is anything divided by 0? It's not defined. So yeah, it's just like things like that you tend to know after you do enough stuff because it just pops up all the time. And then so I was able to pull that out. Anyway, let's see how I answer this. For every real number... Okay, there exists a real number A. Oh, yes, I did that. There exists a real number A for which A times X for every real number X. For which A times X equals to X for every real number X. Well, I wrote there exists a real number A for every real number X such that A times X equal to X. So the meaning's the same. I wrote it a little differently, but that's fine. I'm not supposed to suss out exactly word for word what they're going to say in English because there's a lot more variability. It's not as, I guess, not as buttoned down as formal math language. All right, well, let's continue. All right. So we have next... All right. Number 5. For all n containing the natural set, there exists the set of X containing the power set of the natural set such that the cardinality, the size of the set, is less than the natural set. For all numbers containing the natural set, there exists a set which is a power set of the natural set, such that the cardinality of that set is less than the number we start with. So we say for all, right? So what is the smallest number in the natural set? It's 1. So can we have a cardinality that is less than that number? Well, exists an x with the power set of the natural set. So it would have to be 0. That would have to be the empty set. So if we think about this, there exists a power set of the natural set. The set containing the power set of the natural set. So this either is going to come down to being true because of the empty set, or it's going to be false because you can't have a cardinality smaller than 1. So, like, let's start this I'm just trying to solve whether it's true or false yet. And this shows you my own personal weakness of reading logic, is that it's just like I'm not as well versed enough to where I can just know precisely what it's trying to nail down here. But we'll know in a minute here. We'll know right or wrong. So I just want to still suss it out. We have, for all the naturals, there exist in the natural set, for all numbers, let's say the number's 1, because we want to break this one way or the other, or prove it to be unbreakable. Exists the set containing the power set of the natural set. So, and then that power set, or the cardinality of that power set, is less than the number we started with. So we're talking about the whole cardinality of it. So if the number that we had was 1, the cardinality would have to be 2, I think, because you would have to have wait a minute. No, it wouldn't be 2. It'd still be 1. When you're talking about the cardinality of it, the empty set wouldn't count as part of the cardinality. Cardinality simply is counting the number of items floating in the box. In this case, I would say no. This is false. False. Consider n equals to 1, and there can't be, yeah. All right, so yeah, let's write this here for every natural number n, there exists a set X whose power set with a power set of the natural set. Again, I'm just going to write what they have written out here. Set with the power set of the natural set. It might be a little verbose, but you know what? Well, at least we're not going to leave anything to chance. Such that the cardinality Nullity of the set X is less than the number n. Okay, so wow, that's a paragraph. All right, let's see what they said. Yes, so the 5. Wait a minute. Empty set. Yeah, that's what I was saying. This is why I got it wrong, but that's fine. I figured it was going to go one way or the other. And this is, we're going to say true. Consider the empty set. But that's how you learn. You got to make mistakes. Not intentionally, of course. Consider the empty set. Okay. So we're going to read this. For every natural number n, there is a subset. There is a subset X subset right, we're talking about subsets. That's where I got where did I get the subset wrong? Hang on a minute. Yeah, I read it wrong here somewhere. Oh, the exists a set containing the power set of n. So if it's a power set of n, that means a subset of n. And if it's a subset of n, then yes, it would, the lowest subset you could have of a natural set would be the empty set. So that's very good. This is a subset. Okay, so let's see here. For every natural number n, there is a subset X of, take all this out. It was a subset question. That's what I messed up on. Okay, that's fine though. All right, here we go. Okay, for every natural number n, there is a subset X of n of the natural set with, now the cardinality of X being less than n, they can just do this with cardinality of X is less than n. If you have like an equation like that, you can write that out. This is what they did here. They simply put that equation popped it right in there. That's fine. But if you were going to write that out word for word, we would say with the cardinality of the subset X being less than the number n. And yes, so when we talk about the subsets of a natural set, what would they start with? So we're going to say, let's write the power set of the natural set. Power sets of, so this is a power set of the natural set. And then, we're going to say this is a power set. So the first set right here, that's the one we're talking about. That's the empty set. And then we're going to say 1. So we have the singletons, and then 2. We have 3, and then this is going to go on up until 9, 10, and then we have so yeah, essentially what we're having is and the natural set can have more than one number in it. So you can have because these are sets of the natural set. So in that case, it could be 159, not like 159, but as in those 3 numbers. Or it can be 159, and all of that is contained in the natural set, which again does not contain 0, but it does contain the empty set because that is this is a power set. Power set always starts with the empty set. Okay, I know that's probably verbose and just a little mind melty. That's totally fine though. If any of this is just complicated, just you got to put pen to paper and start with a chapter you can kind of understand, preferably in the beginning of the book. Now, I have been working through this book from the beginning, so you could pop into one of my previous videos and see if it makes any more sense. All right, so that answers that. Let's go to the next one. Okay, and 7. For all sets X, there are subsets. This is for every subset of the natural set. That means starting with the empty set. There exists number n containing the integers such that the cardinality of X is equal to n. So for all of X contained in the natural set, this is a subset symbol right here. This is a subset. So for all, let's just write this out here. We're going to say for all subsets, and then let me see here how we did this. Did we write subset X or just subset? So subset, yeah, we do have to mark it for all subsets. Subsets X. No, what am I here? No, actually, it should be fine. For all subsets of the natural set, for all subsets of the natural set, there exists an integer n. We're just going to write this such that the cardinality of X, the cardinality of the subset is equal to the natural set. So what are the options there? So the empty set could be thought of as 0 because it's empty. So for all the subsets of the natural set, well, what do they start with? They start with the empty set, and the equivalent in an integer form would be 0. And the next subset would be the singletons, and the cardinality, or the size of the singletons, is 1. So that means there exists that. There's that integer. What about, say, what is the cardinality? This is still a subset of the natural set. But let's say that number is, we have 1, 5, 4, 2, 9. We have 5 numbers. The cardinality will be 5. And that is in the natural set. There is no negative sets. So the cardinality, there exists an integer n such that now n is an integer. If it was a natural number, I would say no, it would be false because you'd need 0. And that's what tripped me up on the previous one, but we're using it right here. So I would say this is true. Yes, true. With the set, which is equal to 0 or in the You know what? I'm gonna just, yeah, with the smallest subset being the empty set or 0. Yeah. I'm just gonna take that last part out. Just gonna stop at 0. I try to keep my explanation succinct. Yeah, I know it sounds funny, but I meant like when I write this stuff down, like when I talk, yeah, I can be verbose. But when you write it down, just the less is more. You don't want to leave anything behind. You want to be precise though, because otherwise you're going to trip yourself up. All right. And speaking of leaving stuff behind, that was number 7. Let's see what they say. And so I said that was true. A minute. So hold on. I got it wrong. Let's first read. Did I write it right? For any subset X of n. For any. Oh, I'm in here. Let's see. For any subset. For all subsets of a natural set. At least that's close enough. Let's see if that's close enough. For any subset X of n. For all subsets X of the natural set, there exists an integer n for which the cardinality of x equals to n. So that at least that part I got right. Now let's see here. Then we have the same as false. For example, the set x 2, 4, 6, 8. So the basically evens of all even natural numbers is infinite. So there does not exist any integer n for which cardinality of x equals to right, because because what is infinity? Infinity is infinity. It's in regards to set theory, infinity is it's not like a number. It's not a fixed number. You can think of it that way. It's more like a quality of the set itself. So you can't pin it down to a single number. Let's just correct this part. All right, we're just gonna go in here and we're gonna say false. Okay, now what's interesting is you could have, because the natural set is infinite, you could have a subset that's also infinite. Now a subset can contain the whole set. For example, the naturals is a subset of the natural set. The whole set is its own subset. It's part of it. Just like when we were writing our subsets, the last one would contain the whole. So in this case, though, we can say, like I said, we can say the odds, false. Subsets, false. The natural set contains infinite subsets such as the evens. Let's say even naturals. The even naturals that can't be quantified. I gotta be careful using the word quantified because we're using quantifiers here. Quantified by an integer because infinity is not one number. Because infinity is not an integer. Let's try that. Because infinity is not an integer. Now, the integer set is infinite, but infinity itself, again, it's a quality. It's not a number. So keep that in mind. Like, well, you could subtract like 5 from infinity, and it'd still be infinity. You could add 10 billion to infinity; it would still be infinity. It's a quantity, or it's a quality of being, ever growing or ever shrinking. Infinitesimals would be that. Like infinitely subdividing, for instance. Okay, let's continue here. All right, 9. Last one. Let's see if I can get this one right. Okay. For all naturals, for all numbers n containing the integer set, there exists the number m. There exists a integer m, comma, where m is equal to n plus 5. Okay. So this is, remember a while back we had to do something similar to this, and I said the way to crack something like this is if you can create 0, 1, and -1, and from then on you could essentially assemble any real number that you wanted. Not real, but I mean in this case integer number that you wanted. So if we can show this, so let's play around with it, see what we can do here. First let's write this out. For all integers n, there exists an integer m such that m is equal to n plus 5. Okay, so what if m is 0? For all integers n, there exists an integer m. Okay, so for all integers n, so we're solving the one that we have, the m is the output. We have to crack it so that we can't get it. So if n equals to 0, m is 5. So there exists that, so 5 is equals to n plus 5. So for all integers n, wait a minute. This is suspiciously familiar. For all naturals n, yeah, we had one very similar to this, I think. The example 2.7. For all x containing reals, exists a y containing reals, such that y squared is equal to x. So we have to be careful for no matter, that's a true statement. So for all containing integers, yes. So first I'm just seeing if this is a true statement or not. Trying to figure that part out. as long as, so this is fine because for all integers exists a number with the property such that any of that number n for all of them, you can make n anything. You add 5 and you're going to get m back. And it has to be in the integer set, so it can't be a fraction. But since we're starting with an integer, and then we are adding 5 to it, we're not doing anything special. All we're doing is an integer plus 5 what pops up some other integer. That's all it's trying to tell us. Is it true that if you take any integer you could think of, so let's take -1, you add 5 to it, will you get another integer? Yeah, you will. It'll be 1 plus 5 is 6. What if this is -1 plus 5? Okay, that's 4. So yeah, if it's 0, we get 5 back. So this is true. True. Adding 5 to any Okay, true. Adding 5 to any integer n will give us a new integer m. Yeah, why not? That seems to make sense to me. Let's find out what the book says. For every integer m, there's an integer n such that m equals n plus 5. The statement is true. So they just said it's true because of course it is, right? You're not doing anything magical to your starting integer, just adding 5 to it. And yeah, that's not going to crack it. There's no way to do anything that's going to crack that. That's fine. So got that one right at least. All right. So yeah, we got through this. That was 2.7, and I hope you had fun. I certainly did. All right. So I don't know. I'll see if I can stretch. It's getting a little late now. It's almost midnight here. I got to go to work early. But tomorrow, I'm going to try to do 2 chapters. I can probably stretch 2.8 for half an hour to an hour to really... It's only 2 pages, but I'll try to develop some of the stuff. There's no questions there, but there are plenty of examples. This stuff's pretty dense. And 9... Yeah, 9 is negating. Okay, so yeah, this is, we're going to be flipping the E's and A's, I believe. That's probably what it's going to take. So this is, yeah, that should be good. So hopefully tomorrow we'll get through 59, page 59. That would put us onto 2.10. And then that, you have 10, 11, and that gets us through, oh, that's interesting, 11, 2, and 212 again. So basically, we just have maybe 2 more sections. We have 9, and we have 2.9 and 2.10 are the only questions we have left in the whole chapter 2. It actually goes to 2.12, but 8, 11, and 12 are just examples with no questions involved. So, yeah, I'm going to try to make the most of it, but looks like we're going to be in chapter 3 before the week's out. Yay! All right, tune in tomorrow, and I will see you next time.